going to begin our next section in Chapter 8 on partial fraction decomposition. Now that sounds worse than it really is, and that's not a very good C right there, is it? Let's see what we can do to make that a little bit better. But it's kind of the reverse of what we've done with fractions all these days. Back in grade school, you learned how to add and subtract fractions by getting common denominators and then adjusting the numerators, and you know the steps from there. But now what we're going to do is we're going to try to reverse it, and we're going to have a rational expression or a fraction, and we're going to break it into a sum or difference of simpler rational expressions or fractions. And since it wouldn't be much fun with just fractions, just numbers, we're going to stick with rational expressions. So there are a couple steps that you have to do. The first step is the one I'm going to show you right now, which is to set up the form for a decomposition. And the other is to find the constants, and that's going to make more sense when you see the first part, when you see the form of the decomposition. Because if we were looking to, let's say for example, add a couple fractions that adds up to 2/5. Okay, well, let's not make it 2/5, let's say 2/15. We probably wouldn't be looking for fractions with denominators of 7. We would be looking perhaps for fractions that had denominators of the factors of 15, 3, and 5, and then see if we could get a combination. To get 2/15, we probably have to have one of these maybe being negative, but we would go through those kinds of steps. We want to look to see what factors our denominator is made up of, and then see if we can break it into simpler looking rational expressions. So the first example here that I have, the denominator is already in factored form, which is great. Each linear factor is, there's only one factor of it, to the first power to the first power. So what we're going to do to set up the form for partial fraction decomposition is to use those denominators. Use 3x plus 1 and use x plus 4. It doesn't matter which one you put first. Now the degree of my numerator is 1. This is x to the first power. If you multiply this out, you'd get a 3x squared. The degree of my denominator is 2. When the degree of the numerator is smaller than the degree of the denominator, we consider this a proper rational expression. And we have to have simpler looking rational expressions that are also proper. So these are degree 1, both of these. So that would mean that the degree of our numerators would have to be smaller than 1, or degree 0, which means they're constants. So I'm going to use capital A and capital B here to represent the constants. And that's the form that we would use for the decomposition. Now, there are several steps to actually solve for these constants and such, including using systems of equations, which we're going to get to in just a little bit. But that's the form for the setup. Notice that the denominators are these two factors right here. Now, in this one, it is not in factored form. That's your first step, is to put it into factored form. Not the numerator, the denominator. The denominator I can factor out an x, and that would leave x squared plus 4x plus 4. But this trinomial factors even further. This factors into x times the quantity x plus 2 times the quantity x plus 2. Or in this case, I'll write it with the exponent, 2 factors of x plus 2. Now notice that the factors in my denominator here are still linear. This is linear, this is x to the first power, and x plus 2 is linear, even though there are 2 factors of it, each of the factors are linear. So what I'm going to have here is I'm going to use kind of the same approach here. I want to use each of the different factors. So I want to use the x, and I want to use the x plus 2. But since I have a repeated factor here of x plus 2, I have to include the possibility that the denominator might be that repeated factor. So this only happens on repeated factors. Now if instead of a 2, this had been a 3, then I would have had this, I would have had this, I would have had one more fraction with x plus 2 quantity cubed. You would take every power up to whatever that exponent is. So this is linear. This is linear. And even though if you squared this out, you would get a quadratic, the factor is linear, so I keep a constant factor for the numerator. A, B, and C, there are no variables there. The variable is x. Therefore, they're all considered proper rational expressions, and these are all considered constants, a, b, and c. Now in this example, this is degree 2, this is degree 3. Again, it's proper. So what I'm going to do is I'm going to factor this denominator. Now I know this is kind of different than what you're doing. You may have seen this in a previous math class, but I kind of doubt it. X squared plus 3. Now this factor of x squared plus 3 doesn't factor any further, so we only have these two factors. This one's linear, but this one here is quadratic. So I have the linear and I have the quadratic. Now remember, this was proper here, so these have to be proper. Since this is degree 1, this has to be degree 0, so I'll just use A. But since this is degree 2, this could be as big as degree 1. And if it's as big as degree 1, it's linear. So I'll have to write something that looks like this, a linear expression, where b and c represent some constants. X is my only variable. So when you have a factor that's an irreducible quadratic like this is what the numerator is going to look like. And you can have repeated values of that. In fact, look right up here. In this last example up here, the denominator is x squared plus 3x plus 6 quantity squared. Now x squared plus 3x plus 6, you think, well, maybe that factors. It doesn't. So what's going to happen here is you're going to have two denominators, one being x squared plus 3x plus 6 to the first power, but the other one being x squared plus 3x plus 6 to the second power, because again, it's a repeated factor. Now this is quadratic, so this has to be quadratic, ax plus b. And even though this is technically to the fourth power, my factor is quadratic, so I don't want to use a and b again, so I'll use cx plus d. And as you can see, we started out with an example that only had two constants to find. These two had three constants to find, and that one's got 4. So they can get kind of complicated. You can be at this for a little bit. Just to give you a taste of what's going on before we do a whole bunch of partial fraction decomposition, we're going to go ahead and do this one in the space that I have remaining. But look again, the first thing you want to do is you want to set up the form. So make sure the denominators are factored completely, and then look to see what kind of factors you're working with. Remember, linear factors, it's just a constant. Quadratic factors, it's going to be a linear expression. You're going to have two terms, the one term with the variable and then the constant term. So be careful there. So let's just do this simpler one here. I'll bring it over here, and I'm going to actually find out what a and b would be equal to, what numbers they're equal to, so that this equals this. I'm breaking it apart. I'm taking a messier looking rational expression and breaking it into a sum or difference of simpler rational expressions. Decomposing it. That's the name. So in this case, I have the opposite of x plus 18 is all over the quantity 3x plus 1 times the quantity x plus 4. And we already know that we're going to use this format right here. A over 3x plus 1 plus b all over x plus 4. Alright, now on the right side, if I was going to actually add those, I would have to get a common denominator. And my common denominator would be their product. It would be this guy. So what I'm going to do first is I'm going to rewrite this so that I have a common denominator. So I'd have to multiply top and bottom by x plus 4 on the first one. And I'd have to multiply top and bottom here by 3x plus 1 on this second one. So 3x plus 1 times the numerator times the denominator. I'll write it first so that it's consistent with the other denominator. Now, I have a common denominator. I can put it all over that common denominator, and I'll see if I can simplify when I add the numerators. So I have a little distributive I can do. That's ax plus 4a plus 3bx plus b. Now I'm going to go an extra step here. And after you do a few of these, you'll probably combine a couple of these steps. But do you see how these two terms have the x? They're like terms. These two terms don't have the x. They're like constants. So they're like terms. So I'm going to combine these. Okay, so this would be, well, these two here. Notice they have the x in common. So this would be, you ready? A plus 3b x. That's these two guys. Drink this in, okay? And then over here, plus, and you don't have to put the parentheses around it, but I'm going to emphasize it, 4a plus b. Now remember, that equals this. This is what we started with. I just don't know what a and b are. But these two things should be equal. Well, they're equal, they have the same denominator, so therefore the numerators must be equal. So I look here, what's the coefficient of the x? -1. What's the coefficient of the x? A plus 3b. If these numerators are equal, the coefficients must be equal, the constants must be equal. So I'm telling you here that a plus 3b, that's this guy right here in front of the x, has to equal this constant that's in front of the x, which is -1. And that this constant term right here has to equal this constant term, plus 18. So that gives me 4a plus b is equal to positive 18. And now, I finally have gotten it to something that I did back in section 1. I have a 2x2 system I'm going to solve. In fact, I'll probably just take this top one right here. I'll multiply by -4 so that the a's will cancel if I use the elimination method. -4a minus 12b is equal to positive 4. Don't forget to multiply both sides every term. Leave this one the same. And if I add, these cancel. I get -11b is equal to 22. b is -2. So I can take that and go back to either one of these. It doesn't matter which. I'll just take the bottom one. I will plug a -2 in. And I get, well, if I add 2 to both sides, right? I get 4a is equal to 20. Divide by 4, I have a is equal to 5. Those are my constants. Now don't stop here. I'm circling them, but that's not what I want for the final answer. I want you to write out what it's equal to. So this guy, remember, is equal to here. Well, what's a? Positive 5. B is -2. So this thing is equal to, and I guess I should restate it down here. So negative x, or the opposite of x, plus 18, all over the quantity 3x plus 1 times the quantity x plus 4 is equal to a over 3x plus 1. So that's 5 over 3x plus 1 plus, and then b is -2. So to be plus and negative, I'm just going to write minus 2 all over the denominator of x plus 4. Now, again, back in the review chapter, we took expressions like this and we combined them by getting the common denominator, and we would end up with this as our answer. We have just reversed the process. Now, you may wonder, why would we ever want to break it down into simpler looking rational expressions? The name of this class is pre-calculus. In calculus, one of the integration processes is integrating rational expressions, and some rational expressions are very difficult to integrate. So we may be able to decompose them into simpler ones to make the integration process easier. So you will see this again, probably in Calc 2. Depends on where you're taking calculus. Sometimes they squeeze it in at the end of Calc 1, but usually it's in Calc 2 with the other techniques of integration. So this is a method that we're going to practice, and this, believe it or not, is one of the simpler ones. Look at these guys down here with extra variables. They're going to take even more steps of solving the system. So we need to practice this, and I'm going to show some more examples here in the next video.